Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is John from Business Review, and I will be your host. It is our pleasure to have DeltaTek with us today, who will be presenting this webinar titled, The Cure Report, 70% Rigs at Time Savings. Today's guest speaker is Tristram Horn, CEO of DeltaTek. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We will allocate some time at the end of the session to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But for now, please allow me to welcome Tristram Horn.
Yes, thanks a lot for that kind introduction, John. My name is Tristram Horn, and I am from DeltaTek, and delighted to be speaking to you today. I can see there's a number of participants dialed in from the Americas, so a very good morning to you all. Both the north and southern continents, and a very good afternoon to all of those dialed in the European sector and East. I can also see that we've got a number of existing users of our technology dialed in, so a special thanks to all of you, and also I can see that there are a number of operators who are yet to use our technology, but hopefully you're here to learn a little bit more about it and see whether or not there's any application for your operations. And I hope everybody gets a great deal out of this session. What we're going to be speaking about in this story over the next 30 minutes or so is one which is quite exciting. We've got a reputation in the drilling industry, both out with and within, that we are relatively risk averse when it comes to adopting new and novel ways of working. However, the story of DeltaTek's Cure technologies is one that really smashes that reputation to pieces. Having had the first deployment go to 30% of a geographic market within as short a space as 9 months. And that really does demonstrate the compelling story of just how excited not just DeltaTek were about it, but also the market and how receptive the operator community has been to this new way of working. Now, without any further ado, we'll get going. I appreciate everybody's busy, and we'll don't want to take any more of your time up than you've kindly offered. So let me introduce DeltaTek as a starting point. Who are DeltaTek? Well, DeltaTek are a technology-providing oil and gas service company with the ethos to save rig time from subsea well construction through the deployment of our novel cementing systems, SeaCure, QuickCure, and CallCure. Now, we've been incredibly fortunate at DeltaTek that we've been awarded an industry award, the coveted Energy Voice Gold Award for innovation for our Cure systems. And it's not just down to that rapid adoption that we've talked about, but it's the fact that coupled with that adoption, we've had an impeccable level of service delivery, which is testament to the experienced operational team that DeltaTek have in place. Zero NPT across all 16 deployments that we've had is a massive testimony. And we've, in this journey, established a foundation of quality management systems and environmental management systems that meet the standards of ISO 9001 and 14001, making it possible to cater to a large number of different customers who mandate relatively normal contractual requirements of having these things in place. There was actually the first deployment that was done with Chevron that defined this requirement, which we've taken on with challenge and relish, and that has then enabled DeltaTek to cater to a large variety of clients across different geographic bases. So at the bottom of the slide here, you can see a range of our customers. And At the end of this, we'll be talking a little bit more in depth about the specifics of the case studies that we've done with Siccar Point Energy over the last few months. Here in the UK, which is where DeltaTek is based. We've got a facility very close to Aberdeen Airport, so if anybody's passing through, please feel free to get in touch with us. Now, what is Cure is probably what you're all questioning right now. So what we're about to watch is an animation whereby we will introduce how our stabbed-in inner string cementing system actually functions, and hopefully gives you a good idea as to how this technology works in a subsea environment, technology which is routinely and almost exclusively been used in land and platform-based large bore casing cementing jobs, but not until now has it been so easy to do in a subsea environment. So let's invest a couple of minutes and watch this animation.
At the rig floor, a casing or liner is run with a SeaCure float shoe or float collar, a standard API RP 10F Cat 3C certified double non-return valve, with wiper dart receiver and drill pipe latch-in receiver, complete with backup release shear out feature. The SeaCure assembly, complete with slip joint tool, weight set sub and latch-in adapter, is run into the casing, complete with rupture discs pre-installed. The inner string is run until the conventional load-bearing running tool is made up. With the inner string in tension, the SeaCure slip joint tool is in torque-through position. The inner string is lowered until the latch-in adapter is engaged into the receiver, which is confirmed with an overpull. After the casing is top-filled at the rotary table, the running tool is established into the top of the string, allowing the SeaCure slip joint tool to stroke partially closed into the free rotate position, enabling safe engagement of the running tool. Rotary connections are the seals for the cement job now, taking away reliance on large running tool seals. The string is run in hole to cementing depth where the primary cement job is pumped, following which a wiper dart is launched into the string and chased with slurry to guarantee quality cement around the shoe. Alternatively, a SeaCure ball can be dropped. Once the wiper dart lands and locks into the receiver or the ball lands in the seat, the burst discs are pressure ruptured, enabling the inner string contents to be circulated out by the running tool ball valve, which can subsequently be closed to allow a casing pressure test to be executed with green cement slurry in the borehole annulus, eliminating risk of microannuli development of pressure testing against set cement. Circulation can continue for as long as necessary until the inner string can be recovered. As the SeaCure tool is still in free rotate, the running tool can be safely disengaged before picking up and stroking the SeaCure tool into torque-through position, now able to unlatch from the receiver before pulling out of hole, ready to go drilling straight out of the PDC drillable shoe with no cement plugs or shoe track to damage the BHA or dull the bit, and the casing test already completed.
So as you can see from the animation, it's pretty simple technology, which is testament to why the market has adopted it so quickly. The SeaCure system starts life in respect of a pretty standard latch-in adapter, which has been used for generations in land and platform-based large bore cementing operations. The photograph you can see on the right of the slide here is the SeaCure assembly being run for 9 5/8 operations. The latch-in adapter at the bottom is one which is cut with a DeltaTek proprietary rupture disc, roughly around about halfway up the outer body of the SeaCure latch-in adapter. The system is run with the weight set sub and the SeaCure slip joint tool, as was introduced in the animation, which is the facilitation mechanism that allows this system to be used in any casing or liner string, be it for subsea or otherwise. Now, why might SeaCure be used? Well, fundamentally, by the use of this system, there is no shoe track. And we'll talk in a little more detail as to why that's beneficial on the next slide, where we look at drill out times. But in short, they're pretty quick. And the other factor is that there is no problems with slim hole drill out due to the fact there is no shoe track. Why do people historically always use stabbed in inner string cementing systems where they've had the opportunity? Well, because they understand the benefits that that brings to the cement placement process in respect of minimized cement contamination, and also in respect of the displacement of the cement job. It's no quicker than with a stabbed in inner string cement job. Now, some of the benefits that passes then on to the quantity of the primary cement job is that there's an opportunity to see cement return slightly earlier than we've seen on offsets through the field deployments that DeltaTek have been involved with. And there's the obvious tangible cost saving, but pretty substantially important in today's operating environment is that there's a huge environmental benefit associated with not creating a large cement patio around the wellhead. Now, through DeltaTek's ball drop system, we've had 100% success. Every ball drop SeaCure job has resulted in the surface casing pressure test being executed first time. People's experience of SSR plugs are getting better and better. Some operators will have different experiences than others, but in a nutshell, SeaCure provides that 100% success opportunity, which is attractive to certain operations. On the bottom of this slide, you can see a cross-section of quite an interesting scenario which one of our clients brought to us in retrospect of some of the opportunities that they see as SeaCure bringing to their operations. This picture was taken from a recovered casing string which had a cement job not go perfectly well. In respect of the cement was inside the casing at the end of the cement job. So the operator drilled out the cement and then recovered the casing string. And there was no difference in the drilling parameters to the drill out of this cement than there was to any other shoe track. However, quite surprisingly, when that casing was pulled across the area where the cement was seen and the cement was drilled out, there was substantial quantities of the casing missing. In actual fact, the operator measured the amount of casing missing, and 66% of the steel casing was no longer on the casing and would be normally in shoe track drilling processes somewhere in the wellbore. So in terms of the drill out opportunities that SeaCure brings to the operation, here I've put a couple of our drill outs across all of our deployments. SeaCure shoes drill out in circa 30 minutes on average. Some of the better ones we've seen as short as 6 minutes. On the right, you can see a 17.5-inch drilling out a 20-inch SeaCure, which was incredibly quick. I mentioned about the slim hole drill out opportunity, which SeaCure helps reduce risk of cement blocks falling in around the BHA. This is a drill out on the left that we can see from this, a 12.25-inch assembly drilling out a 30-inch. And a little over 30 minutes, which resulted in all of the operational objectives of that well being achieved. Now, quick cure is something which is bolted onto SeaCure. During the animation, you will have seen the moment in the scenario where circulation continued for as long as necessary until the weight on cement period was over. Now, during this period, SeaCure brings the opportunity, the first time this opportunity has presented itself, to have a controlled circulation path up the inside of the pipe at the end of the cement job. And DeltaTek have been providing a service whereby a heat sweep can be circulated in this controlled circulation path up the inside of the pipe. The warm heat sweep is monitored at the annulus exit of the running tool ball valve so that the exact temperature of the fluid on the inside of the pipe can be measured. And therefore, it can be very simply calculated as to what the temperature transfer through the pipe into the cement sheet in the annulus experiences thanks to the heat sweep. How is quick cure done? Well, very simply, seawater can be circulated through an orifice plate or a shear gun line if the rig is equipped with such an incumbent manifold, which most rigs are nowadays. And this heat up of seawater is done in advance of the cement job, such that at the end of the successful primary cement job, the heat sweep is ready to circulate up the inside of the pipe. The ROV simply monitors the annulus exit fluid temperature through a pre-calibrated subsea temperature gauge, as can be seen on the right of the slide here. And it's incredibly simple technology to minimize any risk of anything going wrong. We as drillers in this industry understand cement theory, and we all know that the most profound impactor on the set properties of cement is down to the temperature. A rule of thumb for this theory is for every 10F or 4.5 C increase in the slurry curing environment temperature, the time to set halves. Now, DeltaTek have worked with just about all of the incumbent major service providers in the cementing space to validate this and perform this in real field deployed scenarios. And we've experienced that through quick cure, early compressive strength development improves by 500% in 12 hours. Transition times are dramatically reduced, and operators benefit from substantially reduced weight on cement times, hence the title of today's webinar. Here is the exact same cement slurry. DeltaTek don't recommend changing the recipe of the cement slurry. All DeltaTek bring to this scenario is this heat sweep and the elevated slurry setting temperature. So here what we can see is the exact same cement slurry subject to the quick cure heat sweep in the top of the slide and then set in the conventional lab test in the bottom of the slide. Now this is where you can see that the compressive strength, or the brown curve, is improved dramatically through the introduction of the heat sweep. The purple line, the transition time, is improved by circa 50%. And this is where operators benefit from the reduced risk of gas in the slurry migrating, and improvement in the weight on cement times that they have to experience. Now, further to the fact that a more structural foundation, a stronger structural foundation is delivered, the experience of some operators by allowing cement to set at ambient temperature is such that not always do the lab results give the exact set times that are experienced in the operation. And this is down to the capabilities of the lab executing the UCS developments. What we can see on the bottom there, whereby an ambient temperature is attempted to be achieved, is that actually a flat line of the temperature can be seen there around about 65 degrees F, which is pretty warm for ambient temperatures in most parts of the world, especially the North Sea or East Canada. And the bottom chart that we can see there actually has an indication that at 16 hours, there should be nearly 1,000 psi of compressive strength in that slurry. This is actually a slurry which was pumped and not subject to the quick cure heat sweep. And we can see from this video that at 16 hours, the slurry at mudline was not necessarily set. See if we can watch that again. As you can see, that slurry is still pretty liquid, so it's not always the case that it's set. Now, sometimes we experience questions from operators of, is the cement adversely affected by the introduction of the heat sweep? And importantly, the introduction of the heat sweep is one not of substantial temperature. DeltaTek recommends starting the heat sweep at surface at around about 65 degrees centigrade. So around about the same temperature as a cup of warm coffee. We're not recommending boiling the cement or exposing it to anything higher than it would normally be exposed to when it's used deeper in the wellbore. But categorically, when in terms of proof in the pudding that this cement has not been adversely affected is the recovery of a core cure cement sample. This cement sample is recovered from the bottom of the inner string underneath where the DeltaTek SeaCure ball lands in the latching adapter and offers a 14-inch cement sample to be recovered back to surface. Now, this cement sample is the sample which is subject to the highest heat of heat sweep. Therefore, gives that confidence that the cement is of paramount integral compressive strength and has not been adversely affected. For any other non-quick cure deployment, core cure still brings benefit in respect of giving confidence that the cement around the shoe has not been contaminated to an extent that you wouldn't have been able to recover the core cure cement sample. For leak-off tests, this could be useful. DeltaTek's Cure operational envelope is growing. We're at 16 deployments now, 0 NPT attributed to the system, and the envelope has been greatly expanded through substantial deep water deployments in the Eastern Mediterranean, where SeaCure was deployed for 20-inch surface casing strings over a kilometre long in nearly 1,800 metres of water with substantial 3,500 barrel cement jobs. The majority of DeltaTek's Cure deployments are now across conductor strings and somewhat shallower 20-inch surface casing strings, but the envelope is well stretched now, and we're confident that we're able to bring the large majority of deployments within this envelope. However, the system is incredibly robust, as has been shown through the deployments so far. And what I want to focus on for the last few minutes is the in-depth analysis of the case studies of one of our early adopter operators, Siccar Point Energy. Alongside Chevron were the first users of the SeaCure technology. And the first deployment which we ran with Siccar Point was on their Blackrock exploration well west of Shetland in the deep water of Q1 of this year, whereby DeltaTek were awarded the 30-inch conductor cement job. The deployment was a great success, the first recovery of core cure cement samples from underneath the DeltaTek SeaCure ball in the latching adapter. What you can see with the pictures on the right of the case study are some of the captures from the offshore deployment. In the top, following the rupture of the rupture disc and the successful internal circulation to clean the inside of the casing, you can see there the ROV's footage of capturing the fluid effluent out of the ball valve. In the middle picture, you can see the SeaCure BHA entering the low-pressure wellhead housing suspended on the clamp in the rotary table, and at the bottom you can see the core cure cement samples recovered at the end of the successful job. Now, the success of the system in this 30-inch deployment, coupled with the problems that were faced during the 20-inch deployment of the use of SSR plugs in the non-bump, led the operator to select SeaCure for both the 30-inch and the 20-inch in their next operation of the campaign that year. DeltaTek were very privileged to have been reselected, as a lot of the customers do. In fact, just about all customers have reused SeaCure following the original deployment. And this is a fantastic example of that reselection. Once again, the 13th conductor cement job was executed flawlessly, and the reduction in planned cement job meant that there was an opportunity to cycle some of that into the subsequent, saving on wellhead patio as well as tangible cost. The 20-inch was an interesting opportunity to realize one of the benefits of SeaCure that wasn't originally obvious. This might be obvious to traditional inner string, pour boy inner string cementing, but not necessarily to those selecting SSR plugs in this scenario. A not abnormal problem was recognized during the cement job, whereby a actuator valve in the bulk delivery system on board the rig wasn't working as per normal functionality in respect of different bulk silos were delivering at the same time to the mix hopper. Obviously, this was not a acceptable way of continuing cement jobs, so the operator selected to shut the operation down temporarily whilst this bulk delivery actuator was replaced. Now, this was 231 barrels into the cement job, a 600 meter long 20-inch casing string, which in normal operational scenarios with an SSR plug, whereby the full casing volume requires to be pumped prior to the cement going out of the shoe and into the annulus. There was an accepting of the by the operator that had that stopped at 231 barrels in, the cement wouldn't have been halfway down the inside of the casing volume at that time. Therefore, shutting down for 45 minutes would have resulted in a detubing and fluid mixing of the front of the cement job. And once the cement job was continued, it would have been an unacceptable risk to have continued with the congealed thixotropic cement at the lead. Therefore, the operator concluded that had the plug job been selected in this scenario, 231 barrels of cement would have had to have been circulated to sea and the job would have had to have been recommenced. However, due to the operator having selected SeaCure, at the point in the operation that 231 barrels of cement had been pumped with a stabbed-in inner string cementing system which has the absolute capability of controlling annular velocities of the fluid, it was perfectly safe to shut down for a temporary period of time to offer the rig crew the time to replace the bulk actuator valve and safely continue with the cement job, not resulting in 231 barrels of cement being circulated to sea with the environmental cost implications. So this really was a feather in the cap for SeaCure earlier in this year, and we've been incredibly fortunate at DeltaTek to have been continually rewarded work by our loyal customer base. And we hope that we continue to be successful in growing the customer base across new customers and across new geographies. So at this point, I would like to open the webinar to questions from everybody in the attendee list. And thank Jonathan for his facilitation of the session so far.
Thank you very much, Tristan. Just a reminder for the audience, in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We already have a couple of very good questions here for Tristan, so I'll start off with the QuickCure heat sweep, how warm is the sweep?
Yeah, good question. So in the 6 deployments of QuickCure that we've done so far, what we've experienced in a surface starting temperature of 65 degrees C has been quite incredibly in 300 feet of water, over 60 degrees C coming out of the cart ball valve. Now, the original modeling that was done indicated that it would probably be a lot lower than this. However, if I flip back to slide 7 here, we can see from the captured ROV footage in the bottom right-hand corner here, the ROV camera witnessing over 60 degrees C on the gauge there from a starting temperature of 65 degrees C. This was against all modelling and was quite a welcomed realisation, as once the calibration was re-put back into all of the models, it was recognised that quick cure with a surface heating system ought to be possible to be deployed in over 3,000 feet of water. So we're very pleased that that capability has been proven through this system. Thanks for that question, John.
Perfect. We have another question here. With the quick cure system, is there any detrimental effect on the cement being heated?
Yeah, good question. And in short, the way that cement hydration theory works is that the cement experiences an initial heat of hydration during its mixing in the mix tub, which is why people will experience quite a warm situation in the cement unit during that initial heat of hydration. When the cement is then pumped downhole and in its liquid state, it doesn't create any further exothermic heat until it starts to set. And it's at that set point that actually big quantities of cement can create even higher temperatures than what we're looking at introducing to the outer wall here. We're only increasing the cement slurry up to between 40 and 50 degrees centigrade. This same style of cement with Portland cement experience substantially higher temperatures when it's used deeper in the wellbore. So we're not exposing it to anything that it's not normally exposed to. All we're doing with the heat sweep is we're accelerating that second exothermic reaction and setting of the cement slurry. Further, it's normally well accepted that cement is used in warmer temperatures than 50 to 60 degrees C. But further evidence that there's no detrimental effect to the cement is the fact that on every quick cure job that DeltaTek has executed in the field, the recovery of the core cure sample has categorically proven that the cement at the highest exposure of temperature is of the highest quality in respect of it has all the compressive strength that one would expect of it without any detrimental effect to that cement. So there's great confidence in that there is no detrimental effect on the cement. That question.
Thank you very much, Tristan. Just a reminder, guys, you can still submit your questions via the Q&A widget. It's just located in the top left-hand corner of your screen. We have another question here. What problems have you had with the SeaCure system?
What problems have we had? Yeah, hey, there's no secrets. During the new technology development phase, things are learned, and we're really proud of the fact that there's been zero MPT associated with the system during its development, during its adoption, during its aggressive market deployment. However, having said that, we have learned stuff along the route, and that is primarily down to the dart and the use of the dart. Now, in the 6, maybe 7 jobs that DeltaTek have done with the dart, the first 2 resulted in the cement dart being lodged in the cement head. And this is something which has been is an age-old problem around our industry. However, with the DeltaTek design review of the dart, in the subsequent deployments with dart, we have experienced 100% success again. However, the recommendation from DeltaTek is to go with the ball on the basis that there has never been a failure with the DeltaTek ball, and 100% success has been achieved. Further, it's much simpler to use the ball than it is with a dart, and the benefit of the core cure is a nice feature as well. Okay, John, that was a good one.
Perfect, thank you very much. We have another question here. Could you cater to our Q2 2020 project spudding in Eastern Canada?
I was hoping for a question like that. Excellent. Well, I presume the question is more in regard to our capabilities and our growth, as we have experienced pretty substantial growth in the development of the technology thus far. Now, DeltaTek have grown the team and grown the capital assets in the organisation to cater to 6 concurrent operations ongoing at any one time across various geographies. So right now, Q2 2020, we have 3 concurrent operations committed to at the end of Q1, start of Q2. So there is some capacity in the organisation to cater to additional spuds if this one doesn't happen to be one of the ones which we're already aware of. You know, we're keen to deploy around the globe and grow the customer base. But paramount importance is the highest standard of operational delivery, continuing our zero MPP track record. Yes, we're really keen to follow this question up in a bit more detail. So thanks a lot for that one.
Perfect. Thank you very much, Tristan. So while I give Tristan some time to read through some of the other questions that have come in, that just leaves me to thank Tristan Horn for what was a great presentation and to DeltaTek for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Perfect. So it looks like we have a couple more questions that have come in. So Tristan, have you compared the additional time to run the inner string versus average time taken to drill plugs shoe track in a standard cement job with no inner string?
Yeah, really important question. Critically, you know, DeltaTek want to engage with operations whereby we know we can add substantial value, and we are not suggesting that is in every cement job. We know that the SSR plug system is the way to go when the length of the casing string is substantially long enough that it obviously outweighs the benefit of running and pulling an inner string. Having said that, where the water depth permits and the inner string can be taken offline, then there's obvious rationale to go with the inner string in that scenario. And we have heard of some scenarios whereby operators do struggle with drilling out conventional shoe tracks. But it's not necessarily always just the raw time that drilling out the shoe track takes when it comes to this analysis. There are a number of other factors which can be weighed into this in respect of how much debris and swarf is introduced to the wellbore whilst drilling a conventional shoe track out. We shared the experience with one of our clients whereby they measured actually on a genuine pulling out of the whole of a casing which has had cement drilled out the inside of it, that 66% of the casing was introduced into the wellbore as swarf and debris during the drilling of inside the casing. And that has the potential ramification to mandate additional wellbore cleanup runs prior to running various completion strings or liner hangers and packers, which is one factor that ought to be considered. Secondly, some operators have experienced BHAs and bit failures of drilling inside casings and inside shoe tracks, which are particularly challenging to do. And some lateral vibrations have caused detrimental effects to BHAs and bits, whereby some operators even do dedicated shoe track drill out trips in order to protect expensive jewellery on subsequent TD BHA drilling runs. And with that in mind, then it's pretty straightforward to build a scenario whereby it's more cost effective to run and pull an inner string than it is to. There's some other factors to consider alongside this as well, which is displacement time of the cement job, which will obviously be substantially shorter with an inner string than with a full bore, especially when you're looking at bigger sizes, 18s, 22s, etc. And some of our deployments have been in order to skip clean out runs of shoe tracks, which are done for slim hole drill outs or undergauge drill outs, whereby operators have cemented a casing string of conventional size, for example, a 20-inch, and then have drilled it out with a 12 1/4, typically that would have been a 17.5-inch clean-out run prior to drilling ahead. Whereas with SeaCure, we've proven that undergauge drilling ahead through the shoe, because there is no shoe track, is perfectly safe. And where you can demonstrate that there's a business case in that, then it can be worth running and pulling an inner string. Hopefully that answers that.
Perfect. Thank you very much, Tristan. We have another question here. How do you mitigate pack-off risk during circulating and not rupturing the disc early, prior to cement displacement?
Yeah, really great question. Thanks to the individual that asked that one. So the rupture disc, which we use in most of our operations, is a 2,500 PSI one. In some scenarios, we've used higher, but the lowest we've used is 2,500 PSI. And one of the tasks that the team do and sit down with the operational engineering team is a PPFG look-see and say, would there be a scenario that can be physically created with the geophysical properties of this wellbore that a pack-off could be created underneath and in the annulus of the cement job, which could rupture the cement job? And if the answer is yes, i.e. the formation is so unbelievably strong that you could do that, then what we simply do is operate the rupture disc. We've never had that scenario whereby we've not been able to operate to an acceptable rupture disc level. The highest rated rupture disc we've used is in incredibly deep water with an incredibly heavy, not incredibly heavy, pre-standard tail PPG, 16 PPG tail, where we went with a 4,000 PSI rupture disc and just worked perfect well. But it's a really important piece of the deployment to consider and engineer into at the concept or the select phase of the project. So thanks a lot for that question.
Perfect. Thank you very much, Tristan. So once again, that just leaves me to thank Tristan Holm for what was a great presentation and to DeltaTek for sponsoring the session. Thank you again to all of our attendees, and I hope you all have a very nice day.